Okay, today is a continuation of our last section where we looked at KSPs, but instead of having the following occur. So maybe silver chloride, if you put that into a beaker of distilled water, you would have 0, 0 plus X plus X. Now, we're going to talk about something called the common ion effect. So maybe this isn't a beaker of water that we put the silver chloride in. Maybe it was a 0.1 molar solution of silver nitrate. Because if we put this into a 0.1 molar silver nitrate solution, we actually have 0.1 molar silver ions. So instead of a 0 right here, it would be a 0.1 molar. If you would add that to X, remember that these K values are very small. So because the K values are very small, this X value is very small. There's a very good chance then that very small value, when you add it with 0.1, is going to give you approximately 0.1 molar. And so that's going to change a lot of ideas here with our solubility. We can also talk in terms of pH. So if the question was silver hydroxide, I guess we don't need that parentheses there. Hydroxide is an item that's going to make the solution basic. pH is above 7. And then if there's a lack of hydroxide, that's going to make, that's because the pH was less than 7. So we can actually manipulate some things about pH. So again, if the pH goes down, that's acidic, and you would have more H positive and less hydroxide. If the pH goes up, it'd be the opposite idea. So you can manipulate the solubility of some compounds like silver hydroxide by actually changing the pH of the solution. Okay, so that's called the common ion effect, and it's a Q versus K idea. This isn't the first time we've talked about Q versus K. So let's go and jump in through a couple questions here. And it says 1 of 4, and I lied. I think it's going to be 5 questions. Okay, so the first one's multiple choice, and like always, we have the answer already. So the answer is going to be C. But let's talk about it. We have excess NaCl. So there better be Na positives and Cl minuses in the beaker. This one here doesn't have any Na pluses. So we've already eliminated one just by looking. It says excess. And then what else? We have AgNO3. The NO3 portion of that is going to be a spectator ion because it's not in the chemical reaction there, but it's still it's going to be in the solution. So we better have some nitrate in there, and it looks like all 3 of these do have nitrate. So we can't eliminate anything else. But if the NaCl is the excess, that means that the AgNO3 is the limiting reactant. And what's really the limiting reactant, since nitrate is the spectator, is a spectator, is the silver ions. So there better not be any silver ions in the beaker. Looks like that eliminates D then. Okay, they all have the right precipitate. Okay, What's the difference between A and C? Let's erase some of this stuff here. Oh, I guess we already know the answer is C. We have NAs and NO3s, but in C, we also have chloride. Remember that it said NaCl was excess, so we better have excess, and that's how we got to C. Question 2 of 4, and I think there's actually going to be 2 of these questions, 2 of 4. Okay, write a balanced chemical equation for the dissolution of calcium hydroxide. We've done this a number of times here. There we go. So that's A. And then B is molar solubility in a 0.1 molar calcium nitrate solution, meaning that we have 0.1 molar calcium ions. Still have 0 for that. Plus X, likely that it's going to be about 0.1. We can verify that when we're done. And so we can still solve for X, and X will be our molar solubility. So we have 1.3 times 10 to the negative 6 for the KSP, likely 0.1 molar, and then 2x squared. Okay, so if we solve for x, we get 1.8 times 10 to the negative third. Now, would 1.8 times 10 to the negative third impacted 0.1? Very insignificantly. So we're okay that we made that assumption. And so that would be our answer, 1.8 times 10 to the negative third. So that's a common ion effect. So we didn't start in a distilled water beaker. We had a solution that we threw this calcium hydroxide in. Okay, so now we're going to work with pH. Okay, so we got KSP. Which of the following changes will increase the solubility? So we want this to go more to the right. And by the way, we already have the answer again as A. So what would make it go more left to right? We need the Q to become smaller than K. So what could make that happen? You would have to decrease the concentrations of those things. And it looks like a couple of these things deal with pH. So let's see, including the right answer, by the way. Well, let's get rid of D. Adding magnesium nitrate, that's adding magnesium ions. That would actually make the reaction be less likely to dissolve magnesium hydroxide. Ammonia doesn't have anything to do with those items in the chemical reaction, so that's kind of a gibberish answer. So it's either increasing or decreasing pH. If you decrease the pH, the H positive goes up and the hydroxide goes down, and that's what we had said that we needed to happen. And the real reason, again, is that that's going to make the Q go down because hydroxide is on the top of that fraction there. So that's going to decrease the value of Q in relationship to K. Molar solubility of silver chloride in a silver nitrate solution. So let's write that out for the dissolution. And instead of a 0 for silver ions, we have a 6.5 times 10 to the negative third here. I probably wouldn't have bothered writing these out anymore. And very likely, it's going to be about 6.5 times 10 to the negative third when you add this very small x value. So 1.6 times 10 to the negative 10th for the KSP equals 6.5 times 10 to the negative third times x. And there's our molar solubility. Now, will 10 to the negative eighth impact 10 to the negative third? I don't think so. So we were definitely fine to make that assumption with this question. Oh, got the answer already down there too. Okay. I had us do 3 different scenarios, and I have reconsidered, and we're not going to do that one yet. We're going to hold off until we learn a little bit more as we move forward in this year. So don't worry about that one yet. Pure water, we've done this one before. So by the way, magnesium hydroxide, you have to remember that it makes 1 magnesium ion, but 2 hydroxide ions. So we got the KSP expression. And that's going to equal x and 2x squared. And we already have the answer here at the bottom, but you can do that math just in case and double check. Now, what would happen if the pH was adjusted? So now, instead of a hydroxide value in that 2x spot, we have a 0.1 in that spot. So 1.2 times 10 to the negative 11th is still our K value. We still have X because we don't know magnesium. But we know the hydroxide is 0.1 molar. Not 2 times 0.1 molar. It's told you that it's 0.1 molar. Still have the coefficient becomes an exponent. So that X, so we already have an answer down there. So it appears that by adding hydroxide, which we did, it shifted that reaction over to the left. And how do I know that? The molar solubility went down compared to in pure water. I think that concludes this unit. It does.